Alright, well, good evening everybody. Welcome to Second Saturday. Tonight I'm going to be talking about binary stars, sort of in response to the recent observation of gravitational waves created by colliding neutron stars. You might have heard about it. It was made by the LIGO observatory. So, first of all, binary stars are a system of just two stars orbiting each other. Some famous examples are star Sirius, the dog star, and it has a companion, the much smaller Sirius B, which you can't see with the eye, but we can detect it because of it has a gravitational impact on Sirius. The star Algol is a binary system, and the star Mizar in the Big Dipper is also a binary star. So, those are some famous ones. Binary stars form pretty much the same as normal stars, in that they start out their lives as a cloud of hydrogen gas in space, and fluctuations in the gas cause it to condense. Gravity pulls the gas in towards itself, and when enough pressure builds up in the core of this cloud of gas, fusion begins, and you have a star. And so, to create a binary star system instead of a single star, in the early stages of formation, the early cloud is kind of fragmented, and so you get two protostars orbiting each other instead of just one star. Some people theorize that binary stars could be created by gravitational capture, where one star captures a passing star, basically, and then they become one system. But because binary stars are so common, and that is so unlikely to happen, it's much more likely that binary stars form like the way it's depicted on the board. As you can see in this picture, binary stars can also form accretion disks, so this means they can also have planets. They can have, orbiting clouds of gas and dust, which means binary stars can have planets orbiting them. They're pretty cool. So, how do we detect binary stars? Some of them we can just observe both stars orbiting each other, and those are called visual binaries, where we can actually see both stars. Sometimes we can even see one star eclipsing the other, which is what's happening in the middle there. I think that's Algol, and that's one of the stars passing in front of and behind the other star. It's pretty cool. It's a time-lapse. But if one of the stars is so small that we can't see it with a telescope or with the eye, we can still figure out that it's there, because as the smaller star orbits the bigger star, it, let me see if I can get this. Nope, sorry. That was a GIF. It was really cool. As the smaller star orbits the larger star, it causes the larger star to wobble a little bit. So, over there, the larger star would be the blue one, and that little circle it's on, that would be its smaller orbit, as it's pulled along a tiny bit by the much smaller star. And as we look at that larger star in the middle, we'll see it, sort of wobbling towards us and then wobbling away from us. By observing its spectra, by looking at, like splitting the light that comes off of it into a rainbow, we can observe. We can figure out that it's wobbling towards us and wobbling away from us. So that's how we found a lot of binary stars, because, we can find ones that we can't just observe. So, because obviously binary stars don't have to be identical. If, one can be much larger and one can be very small. In fact, the stars can be in different stages, of their lifespan. So one star could be a white dwarf at the end of its life, and one star could still be, a main sequence star like our sun. Depending on how closely the stars orbit and their masses, the stars can actually share mass. So binary stars can be detached, which is what this is showing over here. The stars orbit far enough away that mass from each star is not pulled towards the other star. They can be semi-detached, which is that center image, where the mass from the stars are pulled towards each other, but they're not close, they're not orbiting close enough for to connect and for them to actually share mass. And then there are contact binaries, which is the image on your right, and that's where the stars are actually physically sharing mass, which is pretty cool. So, why are they interesting? You know, binary stars, I mean, you know, it sounds cool and everything, but they're very common. So why do we find them interesting? Well, it's because when you have two stars in such close proximity to each other, interesting interactions can take place. When it comes to transfer of mass, it can, when stars are sharing mass, it can change the rate at which a star ages, or seems to age. When stars begin to run out of helium, hydrogen and helium fusing in their cores, they expand into red giants. And if there's another star orbiting that red giant, it can siphon off the outer layers of the red giant, making it look like the giant is a main sequence star that hasn't expanded yet. I think this happens in algal as well. And so that's pretty interesting, that binary stars can sort of change, it can act seemingly paradoxically in contradiction of what we know about stellar evolution. But the really cool stuff is when the stars collide, because, you know, that's something that happens when you have two stars sometimes. So one type of interaction is called a type 1a supernova. And so this takes place in a system where one of the stars is a white dwarf. And so a white dwarf is, it's the remnant of a star like our sun. So when our sun ages, in a few billion years, it will run out of fuel to fuse in its core. It will, because our star isn't big enough to really fuse elements much past carbon, and so eventually our star will shed its outer layers and leave behind what's called a white dwarf, which is just the core of the star. And fusion isn't occurring there anymore because it doesn't have the mass to force the atoms together in its core. And so when one of the stars in a binary is a white dwarf, that white dwarf can, depending on how it's orbiting, it can siphon mass off of the other star. And so as that white dwarf gains more and more mass, temperature and pressure in its core rises. And as you might expect, once it gets big enough, fusion of carbon becomes possible in the core. Now, this isn't a very stable process, because, you know, right as fusion becomes possible, it happens explosively. And in, I think, I wrote it down, a few seconds, a substantial amount of the carbon and some oxygen in the white dwarf is fused immediately, which releases a massive amount of energy, as you might expect. And it releases so much energy that the star itself can't hold itself together. And so the restarting of fusion in the core of the white dwarf sends out a shockwave that, you know, explodes the star. And that's what a type 1 supernova is. This is different from a normal supernova, which happens when a star dies and the core collapses, and that the shockwave sent out by core collapse causes the outer layers to explode outwards in a supernova. Whereas here in a type 1a supernova, just the whole star is gone. So when both stars in a binary are white dwarfs, and if their orbits are degenerating, if they're, you know, falling in closer to each other, you get a different result. So white dwarfs, if they're slowly rotating, there's a limit on their size. The largest white dwarf you can have it's rotating relatively slowly, is 1.4 times the mass of the sun. And if the white dwarf gets bigger than that, it'll collapse, because it doesn't have fusion in the center pushing outwards to counteract gravity. So, if two white dwarfs are spiraling in toward each other, when they merge, they exceed that limit. I guess if they're most likely big enough that when they merge, they exceed that limit, and they collapse. And when the core of a star collapses, it sends out a shockwave that explodes out the outer layers, and that's a supernova. That picture over there is, it kind of shows what happens when two white dwarfs spiral into each other. I think it's actually supposed to be an illustration of the neutron stars colliding, but it happens in a fairly similar way, that the orbits degenerate and they spiral in closer and closer to each other. And so that brings us to the gravitational waves. So, neutron stars they're formed in a similar way to white dwarfs, but they're very different. Neutron stars form when a star much more massive than our sun dies, and expels the outer layers, and the white dwarf is what's left of that star. And so it's much more massive a neutron star is what's left of that much more massive star. And so neutron stars are much bigger than white dwarfs, but they still don't have fusion going on in the center. And so what's special about neutron stars that allows them to create gravitational waves when they collide is that they're just so massive and so dense. They might not be huge. An average size for a neutron star is like 1.6 times the mass of the sun, which, I mean, that's pretty big, but it's not super massive. But because mass is packed so tightly in the neutron star, you have the mass of Mount Everest contained in 1 teaspoon of neutron star. They have a lot of gravity. So, when you have two objects this massive, two neutron stars or two black holes, which also have a lot of gravity, or even maybe one of each, when they collide, that causes intense distortion of space-time, because as Einstein theorized, gravity is really just ripples and distortions in the fabric of space-time. And so that's how you can get waves. And because the objects are so massive, their gravity accelerates them faster and faster. So at the moment of collision, the stars or the black holes can be orbiting 1,000 times a second, which is really fast considering that they can be, 1.5 times the mass of the sun, and they're orbiting each other 1,000 times a second just before collision. So this is... Oh, good, it's playing. Okay. This is a really great GIF I found on the internet. It's supposed to be two black holes colliding. And you can see down below there, that's supposed to be the distortion of space-time caused by those black holes. So because they have so much gravity, they create kind of a well in the fabric. And you could imagine it like that. And so when those two very deep wells collide, like right there, that sends out waves in the curvature of space-time. And we can detect that here on Earth. And we actually did, fairly recently. So you might have heard of the LIGO observation, where they recorded some gravitational waves from colliding neutron stars. And while we have observed gravitational waves a few times before, it was always with colliding black holes. And the problem with that is that you can't actually see black holes, because they don't emit any light. And so the only way we were able to detect a collision of black holes was through the gravity waves they produced. But when two stars collide, we can see that, because they're made of matter and they send out fireworks and everything. And so we could actually, I'm pretty sure these are images of what was going on over there. And so not only were the people at LIGO able to observe this collision through the detection of gravitational waves, but also people at the Chandra X-ray Observatory detected X-rays emitted by this collision, and people at the very creatively named Very Large Array in New Mexico were able to observe this collision taking place as well. You might be wondering, what happens when two neutron stars collide? Well, it's kind of like when you step on a grape, and the insides of the grape kind of, spew out the sides. That's basically what happens, except it's neutron stars. So as the stars get closer and closer together, and they're orbiting faster and faster, the outer layers are squished outwards and form sort of a donut-shaped ring around where the collision will take place. Like if you, stepped on a grape, you'd get a donut of grape debris around it. And then when the stars actually collide, it sends shockwaves through the rest of the star, and that ejects some material from their poles. But because they're spinning so quickly, and because they're made of charged particles, there's crazy magnetic fields around the neutron stars, and so the matter ejected from the poles gets trapped in that, and it interacts with this like donut-shaped ring around the center of the neutron stars. And we can observe that. Because there's so much energy going on here, and because the stars were orbiting so quickly, they're accelerating matter and energy to very high speeds, close to the speed of light. And so that's what emits gamma ray bursts and X-rays, which are very high energy radiation, and that's what they detected at the Chandra X-ray Observatory. Some X-rays. It's kind of their job. So, not only was this cool because we could see it, but it also answered a lot of questions about formation of elements. So, elements like gold and silver, heavy metals, uranium, they take a lot of energy to form. Our sun can only make elements as big as carbon or oxygen, and those are tiny compared to gold. Does anyone know what gold's atomic number is? It's double digits. I can't remember it, but I think it's in the 30s. And so it's a much larger atom than carbon, whose atomic number is 6. It has 6 protons. And so it takes more energy than any star could create in its core to fuse atoms to make elements like gold and other heavy metals. Okay, yes, question.
The atomic number for gold is
79? Okay. I was close. Anyway, it's, what's that?
You were off by around 39.
Thank you. So it's a massive element. And so people, that was a mystery how gold is created, because stars can't create them in their cores. Some people thought that maybe when a star goes supernova, that's where those heavy metals were synthesized. Because a supernova does produce a lot of energy, but it's rare. It's rare that one would produce enough energy to fuse all of those metals. There just aren't enough super powerful supernovas to account for the amount of gold and silver and iridium in the universe. But the LIGO observation gave evidence to another theory that colliding neutron stars like this could synthesize elements like heavy metals, because this generates incredible amounts of energy, more than a supernova of a normal star. It distorts the fabric of space-time. That's how much energy there is. And so we can, because we can actually observe this event, we can try to figure out, what kind of elements were produced here, and whether or not this kind of collision can account for the amount of heavy metals there are that exist in the universe. So, that kind of leads us to the future of binary stars. So, obviously, we've only observed gravitational waves a few times. I mean, I think, was it last year that we saw them for the first time? It was very recently. And this is, and the LIGO observation was the first time we saw a collision, or the creation of gravitational waves visually. So, if we want to discover more about how heavy metals were created, we probably need to observe some more neutron star collisions. It'll probably take a while. And we can also continue to study the most recent collision. And there's also still a lot to learn about the formation of binary stars and their lifestyles. When you have two stars together, they just, they do really interesting things. And to finish off, this is a picture from the one of the Star Wars movies. That's Luke Skywalker living on a planet with binary stars. So those are binary stars. Does anyone have any questions? Yes.
Okay. What's the distance between these binary stars? I know it's going to vary, but what are we talking? Millions? 100,000 miles? Or how much?
Well, I'm trying to think. I mean, it really depends. Depending on... that's actually a really good question. I don't know exact numbers. I don't think it could be... Yeah, that's a good question, and I'll get back to you on that. I know that the orbit periods vary vastly. Stars getting close to, or binary stars getting close to colliding with each other could have an orbital period of like a couple minutes or a few days, whereas other binaries that we've observed have orbital periods of thousands or millions of years. So there's a lot of variation. Yeah. I'll get back to you with it. I can look it up and get you some exact numbers, but it varies wildly. Yes.
When they collide, do the heavy metals get vaporized, or do they get dispersed into the universe?
What happens is when they collide, the elements, because the heavy metals don't exist yet in the neutron stars, because the neutron star is what's left over after a much larger star dies. And that much larger star didn't have the energy to create the heavy metals in its core. So there aren't any heavy metals yet, although there might be, larger elements larger than carbon, maybe iron. But when the two neutron stars collide, there's so much energy that it can fuse smaller elements to create the heavy metals. That's how, and then I guess it gets dispersed with each collision. Yes?
For the LIGO observation, about how close was that to Earth?
Fairly far away. Was it? I think it was like 130 million light years away. So, pretty far. You need to, a couple weeks away. Maybe take a plane, not a car. Yeah, it'd take you a little while. But that's, it's relatively close compared to, some of the other things we observe, which can be billions, tens of billions of light years away. Anybody else? Any other questions? Alright, well, cool. Well, thank you so much for coming out tonight. You can visit us online. We're on the internet. We're on Facebook. We're on YouTube. I personally am on YouTube right now, streaming. We have an email. And next month there will be another installment of Second Saturday Stars. Thank you so much.